Okay, hey and welcome to example 8. In this one we're going to create a spark hit that is very common to use in production, especially when I worked on transformers. We did a lot of these things, but yeah. So here's what we're going to create. It's a simple spark hit from the ground. And this can be baked down to a tool that we used for interaction between characters or anything you really want. I'm going to show you guys how to emit the particles and how to set up the velocities, and also how to copy on these lines and create the color. Regardless, if you want to do with the lines or if you want to render with motion blur, that's up to you. It kind of depends on your shot and what's going on with the camera. But sometimes when the camera is really moving a lot, you kind of want to disable motion blur on the particles because it's going to look really weird. It's going to look correct, but still really ugly. So it's kind of like a decision you have to make if you want to make them correct or if you want to make them pretty. But yeah, so I'm gonna walk you through this, all these nodes. This is set up. It's kind of short, but still, it's gonna learn all things. So let's start off. We're gonna create a sphere in the middle in position 0, 0, 0. We're gonna do a mountain, add some noise to it, like this. Just simply play a little bit with this, with the height to 1. Then we're gonna transform it, shrink it down. So in x-axis it's 0, but it keep the same scale in these two, and then scale it down uniform to 0.5. This is to get like all the particles on the actual grid, to get them in 0 in x in y, because it's gonna be easy to work with. Then we're gonna scatter some point with scatter node. I just choose a random value here, 2, 3, it's fine. And then we're gonna disable the relaxed iterations because that makes everything slower. So we're gonna disable that because we don't need it. And then next up, we are gonna scale it down a little more with a transform node, because this was a thing I just realized now, kind of. So I scale it down 0.5 again and scale it up to yeah, scale it down 0.5 to make it a little bit smaller, to make it from like a centered point instead of like a bigger area. And that's it for the source for the particles. So now we want to set up the velocities. We want to set up velocity vectors that these particles are going to use as our initial velocity, and we want them to be kind of interesting. We want them to be not totally random, right? We want them to be a little bit controlled, but still really like pointing towards different directions, and clusters of high velocity ones and clusters of low velocity particles, and like we want to make it look interesting. So a way to do that is to create the velocities in a volume warp, in a point warp, sorry, before we go into the dot net here. So I'm going to show you guys what the velocity will look like. I'm going to visualize them using the normals, because the normals show a more accurate representation. The velocity or v vector when shown in the viewport is kind of small and like kind of hard to see how it will act, but therefore you can like just pipe everything you do to a velocity, you can pipe it to a normal as well, so you will output it and you can see it in the viewport. So if I go to the create v point pop and I turn on visualize normals, we can see here. So these are the kind of normals I'm talking about. Like we want these kind of like two big pointy ones here. We want some smaller ones in the middle, and we want them all to like different directions, and we want them to kind of have organic feel to them still. So not totally random, but we want them to be like an interesting random, sort of. So how can we do this? Well, let's dive into the create v point pop and let's take a look. So creating random velocity like this is very useful to use the turbulent noise node. Okay, so if you pipe the position to the turbulent noise, and in here we're gonna set the frequency a little bit higher. We're gonna set it to let's say 5.1 for x, y, and z. Doesn't matter. Amplitude, keep it at 1. Change the signature to 3D noise. Change the noise type to sparse convolution noise. You have to be careful when you hit sparse convolution noise, because this noise goes from values from -1 to 1. And since we don't want any particles to fly downwards, we kind of have to be mindful of that at the end, okay? But for now, our values coming out of this is going to be between 1 and -1, so we have to just keep that in mind. Next up, we want to correct this. So to correct this, while still keeping it as a sparse convolution noise, but still keep the y values in a positive direction, we're going to split the vector up with a vector to float. So what it does is it takes the vector and it outputs the float for each axis. So x, y, and z. So x and z is fine. We don't have to mind them, okay? But in y, we kind of want to make all the values we have, negative or positive ones, we're gonna make them positive. So how do we do this? Well, it's quite simple. So all we need to do is we need to pipe the y value into an absolute node, like this. This will take any minus value, let's say you have minus 0.5, and make this value 0.5. So we make every minus value into a positive one. Also, I decided here that I don't want any values that is 0 in y to exist, because I want all of my particles to fly a little bit upwards. Therefore, I have my absolute here piped into an add, and I have to the add, I'm adding 0.3. So let's think, if a point here coming in here, it still do all of this, like terminal noise and shit and absolute, but it comes out as a 0 here. I still want to add 0.3 to this 0 to ensure that every particle is going to fly at least upwards in y, okay? Then to put all of these vector values together again, we have to do a float to vector, which is the reverse of a vector to float. This one takes 3 inputs and outputs a vector. So it takes x, y, and z. So as I said, x and z in this one is fine. We don't have to worry about them. So x, we're going to pipe to x, and z, we're going to pipe to z. And then we pipe the add into the y value. And our vector is now put together again. And as I said earlier, I like to visualize my vectors with the normal in the viewport. So I can pipe this vector to both velocity and to normal. It's your choice to go ahead and, when you're happy with these vectors, you can see them here. You can easily just take this off and never mind them again. If you want to, you do anything else with your normals. But I'm going to keep it like this. I don't really mind. I'm not going to do anything for now with my normals. But yeah. So make sure the vector is going to both velocity and normal to kind of visualize them and use them in the pop system later. And that's it for setting up our normals. If we're happy with how they look, we can also do this. So we have our noise here. We can promote the offset. And if we want to kind of, I'm not sure so happy with these. I can kind of go here. I kind of play a little bit with this one. And if I find something more interesting, maybe this is more interesting what I want. Not really, but let's say we do this. And we kind of do it like this. Let's try to find something cool. Maybe this is what I want. I don't know. Well, it all depends, right? But I'm gonna keep it at my original one because I think this looks the coolest actually. It's really weird how you can initially find something that looks best, but yeah. So I'm gonna keep my offset to 0, 0, 0, and that's it. My velocities are created. So now I can go into the popnet. In here, we are gonna do some standard things. We are first gonna take a look at the source first input node. I'm putting the emission types at points, and this is because I want to control kind of the amount in here. I also put in the so the points in birth. This, never mind this, but in the constant activation here, I have kind of like a H script that says a couple of things. So I'm gonna go over this with you guys really quick. So let's add a note here and let's think about this. So $F gives us the current frame we're at. And if I type $F is greater than 5, that means I'm gonna look at all the frames that are over 5 from the $F value. So the frames before that, I'm not gonna look at all, okay? And then we can type something else, which is and, which basically in HScript language, it means and. And then we will type $F is less than 7. What does this mean? That means we're going to look at all the frames that are less than 7. So what this little sentence here basically means that we are going to look at all the frames that are greater than 5, but also in the same sentence that are less than 7. Okay? this means that our emission frame is going to be only the values that are greater than 5 and less than 7. We can put this to, if you put this to 13, we're now going to emit from frame 6 up until frame 12. As you can see, boom, 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 and at 12 it stops. So let's keep it at 7. But this is just like a little thing I wanted to show you guys to like make it kind of like a short thing about it. But yeah, so I'm gonna put the constant birthday to 9,000. Seems like a good value, whatever. And then I'm gonna do something kind of interesting as well here. So one thing that tends to happen when you have really high velocities is that the first frame of your emitted point is gonna look like this, which I personally don't really like, because it's gonna look like a really weird thing when it just pops on like this, right? So what I like to do is I like to do it with a little trick here I learned. So we are actually going to use the just born group for this to work. So we're going to create a just born group, which means that all the points that are just born at this current frame is going to put into a group. So the first frame a particle is born is going to be in this group. The second frame it's alive in our sim, it's going to be out of the group, which means that we can control stuff on the first frame of the birth, which is exactly what we're doing here. We want to control these particles so they don't look like this on the first frame when they are born. Okay, so we're going to create a group here to call b_birth. Okay, I like to just born groups. I like to do with b_ to kind of, you know, make it like a, so I know kind of what it is. I'm going to put the light expectancy to 0.3 and the life variance to 1. In attributes, I am gonna do an add inherited velocity. I'm gonna multiply it by a value here. I put 7. Yeah, I put some variance. It doesn't matter. Quite high, 2.1. So I get some like normal, like some variance, some random stuff. That's it. But for the B birth, we are now going to correct these particles. So as you can see here, that they're on the first frame they're born, they already have a position that is like way off the grid. I want to get them back to the grid. How do we do this? Well, we can create a pop-up. We can set the group to only work on the B birth, which means it's only going to work on the first frame when a particle is born. So doing that, I correct them. I add them back to the ground, so they are at the 0 value, which means that they will now travel like that, which looks a little more realistic to me. But if you go in here, it's very simple. The only thing I do is I set the y value to 0, or I simply don't do anything with it. You can do a constant here just to make it more. So I put 0. So the x is the same, the y is the same, but the x is the same, z is the same, but the y is back to 0. And I'll put it to p. So my new vector is this. Quite simple. And then I simply add some turbulence to get some more interesting things going on. Put that to 2. Don't really change anything else on the turbulent. And that's it for our pop forces for now. We can choose to add some drag. I cannot create it on some things here, but for this tutorial, I'm not going to turn this on. If you want to, you can go through the scene file and turn this on and see what I did here, but that's up to you. Standard things here, I don't do anything with this. I add in a merge after the pop solver, and to the merge, I add a ground plane for collision. The ground plane looks like this. It's an infinite grid. It's a very fast collision object, which is really nice. You can turn it off by clicking this button so you don't see it, but it's still there. I put the bounce forward to, instead of 1, I put it to 0.85 to kind of limit the friction a bit, or limit the slide of the particles when they collide. I put down a gravity, I put it to standard value 9.8. And yeah, that's it for the popnet as well. So let's see what this looks like when we start simulating here. Boom. It's quite, yeah, looks cool. So we have all the values now, and we have all the turbulent, and we have all the velocities, and we have the gravity working, pulling them down, some bouncing. Looks pretty nice. So now we're on to the second part of this. We want to actually put some geometry on these and put some color on these and kind of make them look more like sparks. Because now they look like points, right? We want to make them look like sparks. Some hot, bright cores and some, you know, some length to it and stuff like this. Those curvy, nice sparks. We want to make that. So to do that, we first want to set up some p-scale. If we go into the p-scale create one, the point up here, I'm going to show you guys how to do this. So don't mind this for now. I'm going to talk about it in a bit here. But first of all, we're going to create a p-scale. So I want both. I want some random p-scale, right? But I also want the p-scale to kind of shrink as they kind of get colder, you know, like sparks kind of fly off. They're super hot, they're super bright, and then they kind of diminish and kind of shrink, and you know, the energy of them kind of lose its value over time. So how to do that is I grab the age from the particles, I pipe it into a fit, I put the source me into some random values. This is the minimum age, which is, I can put it to 0, doesn't matter, but I'm going to put the source max to 0.7. That's not the maximum age of the particles, since you remember we had 0.3 and a variance of 1, so they can actually live for 1.3 seconds. But regardless, I'm gonna say that after 0.7 seconds, I don't really care how their p-scale scales or shrinks, so I'm gonna put it at that and leave it for that. So I'm gonna say that in the beginning, in 0.0, in the age 0, they're gonna have 2, and in age 0.7 they're gonna have 1. So they're gonna shrink an entire value between 0 and 0.7, which is kind of cool. So, but this is not the definitive p-scale. We're gonna use this as a multiplier to our random value. So what I want to do is I want to grab an ID. I'm gonna put it in random, because I remember all the particles that we pull through a particle system gets an ID automatically. This means we can put a random value to each point, and the random goes between 0 and 1. So all the values coming out here is 0 or 1. We're going to put that to our multiply here. And this means that we're going to multiply this value with this value. So some particles that are, let's say, a random value. Let's say we have a point that it comes out with a value from this random that is 0.5. This point is going to get its value multiplied by the current age of it. So let's say the 0.5 starts off, it's at 0. It's at 0, and therefore we multiply it by 2. So 0.5 times 2 means 1. So the p-scale after in the first when the age is 0 is going to be 1. For another point, it might have 0.8, and we multiply that by 2 when the age is 0. Then when the age starts growing, when it comes up to 0.7, we're only going to multiply it by 1, which means that a particle is 0.5 coming out here that was at 0 age, 0.5 times 2 will now be 0.5 times 1, which means that the particle will shrink over time while also keeping a really random start value here. So that's why I do this. And then we output that to a bind and a p-scale. I also want to do another thing. So later on, we're going to copy some lines onto these points. And to get the lines to kind of travel in the right direction, we want them to have a normal that points in the direction that the particle is flying. And the only way to do this right now is to either do some really serious calculations of the point, like where it's traveling and stuff, or we can really roughly just grab the velocity of the point and pipe that vector into the normal. And that means that if we go up here and we turn on normal, that means our normal is also going to change. It's going to fly with the particle and the direction it's flying. And that means we can keep our lines flying in the direction that our particle is flying. So therefore I pipe the velocity into the normal. So we're done with p-scale and the velocity normal transition, Now we're gonna create some colors for our particles. So this is how the color is gonna look. We are gonna try to make them at the first couple of frames. We're gonna make them super bright, super yellowish, almost whitish, and then over time they're gonna kind of flicker a little bit, and they're gonna get colder and more like brownish, orangey, while still keeping a couple of them kind of hot. But in here, like this last couple of frames, they're gonna be almost out of energy. So we really want to convey that like scale and energy conservation over time, which makes our particles look really nice and really, I don't know, not so fake, I guess. Anyway, so let's dive into the CD crate. Here we're gonna do something kind of similar. We want to kind of first of all, we're gonna do the base color. Okay, so if I pipe this ramp here into color, we're gonna take a look at what that looks like. Actually, we can keep it here. So if you go to a random frame, they're not really losing any value. They are simply a color that is assigned to them. And how we do that is we take the ID for each particle, we put it to a random. This random outputs a value between 0 and 1, which is great because that's exactly what a ramp here will take. So we put on a ramp, we pipe the random value into the input of the ramp. The ramp, we can simply pick some colors. I picked a kind of a orangey reddish color here and a more yellowy orange over here. That's only the color spectrum that we're gonna work on here. And that's great. Now we have different values here of color and we're happy. But we now kind of want to multiply some things by age and get some more randomness in there. So at first, to do this, we have our color here. This is all good, all right? Now, we want to kind of multiply by age. So we're going to grab the age, put it to a fit. We're going to put the source min to 0, and we're going to also, at the same time, take a random here. I piped it to ptenum here, I don't know why, but you could pipe it to the ID just as well. I'm going to keep it in the ptenum here. So we'll pipe the ptenum to the random, and then the random into the source max. This means we'll get a value between 0 and 1 for each particle, which is going to be great because we want to have a really, really random value here. So, and this also means that our age will be kind of different for each particle. So the destination min, we want to keep it at 6, which is really bright and hot. This means that our current color here will get multiplied by 6 when it's really young, when it's like a 0 age. And then we want to keep the destination max at a really low value, which means our particles, when they are at a very high age, they are going to be very diminished and not so bright anymore, you know? And then we pipe the fit with these values. That goes between 6 and 0.2 for the age. We pipe that to multiply to the second input, and to the first input we put our original color. And then we're going to pipe this multiply into the color output, and we can clearly see here that our values are now diminishing and are super bright in the beginning. We can even demonstrate this by turning this up by 12, or let's say 50. You can see that our points are super bright now, but they're still dying off here, like that. Put this back to 6. So that's cool. We have our color, we have our velocities, we have our normals, we have our p-scale. Now it's a couple of steps left. We're gonna copy on some lines here, and I'm gonna show you guys how that looks. It's gonna look like this, like that. And as you can see, the p-scale is clearly working. They are shrinking a lot. Go to the null here. And they're also keeping the color and the velocities and stuff like this. If I go back to the p-scale here, completely create, and I turn this off, I'm going to show you guys what happened if I don't put the velocities normal. They will now not really keep the kind of direction, which looks really weird. So this is a very important thing, to pipe the velocity to normal. So keep them flying in the right direction, like that. I did a little bit of work on the lines. I added a line, put it to length of 0.13 and put the points to 10. I add a slight turbulence to the line, just to have some kind of interesting things to it. Like that. Terminal noise frequency 10, amplitude 2, kind of low, almost 0.1. And alligator noise 3D signature, and then add it back to the original position and pipe it to the position. And yeah, that's kind of it. That is kind of it. Yeah. So let's play this one time, and then we can see where we're at. Boom. And obviously you can make it faster, you can make it drag after a while, and like you can make all these kind of interesting things to it. But this is kind of just the basic setup of it, and I had a lot of success with it. So hope you guys learned something. We went over a lot of things. We went over the velocity, the p-scale, the color, and the lines. And yeah, thank you guys for watching. See you in the next tutorial. Bye.